All right, let's get into it. We're talking about turning wasted industrial heat into clean power, all by using a really clever AI. So, steel manufacturing, it's a huge source of CO2 emissions, and a lot of that is just heat, literally vented into the air. But that waste, it's actually a massive opportunity. We're talking 10 megawatts of potential clean power from just one furnace cluster.
So the obvious question is, why not just grab this heat? Well, it's because the source is super volatile and really hard to control. Here's what we'll cover: the problem, the SCO2 challenge, the AI fix, some real-world lessons, and what's coming next. Okay, so a potential solution is something called a supercritical CO2 Brayton cycle. It's promising, but it comes with a catch.
Basically, it uses pressurized CO2 instead of steam. It cycles it through a turbine to turn all that heat into power.
And here's why they're so great. They're super efficient, 100 times smaller than steam plants, and way more cost-effective for this job.
But here's the big problem. The cycle runs right near CO2's critical point, where its behavior gets really weird and unpredictable.
Just look at this. The system's response is completely lopsided. That is an absolute nightmare for any standard controller. And this is a huge safety issue. If it gets too cold, you get two-phase flow. That's part liquid, part gas, which will destroy the turbine.
And that's where the AI comes in. Meet SCO2 a framework built to tame this beast safely and efficiently.
Okay, this is the big picture. It shows the entire system, from simulation all the way to deployment. It's got three key parts: a digital twin for the physics, an AI trainer, and an accelerator to make it all lightning fast. The AI learns step by step. It's a 7-phase curriculum, going from easy scenarios all the way to full-on emergency shutdowns.
So the whole pipeline is you take the physics model, collect data from it, train the AI, then deploy it to the hardware.
All right, that all sounds good, but does it actually beat what's being used in plants today? Let's check out the results.
Right away, the AI beats a standard PID controller, that's the industry workhorse, by a huge 30 to almost 40%.
And get this, it wasn't just better, it was perfectly safe. 0 safety violations across all 140 tests.
But full disclosure, performance did drop in the tougher phases. It's a classic AI problem called catastrophic forgetting.
So they tried something else, training an AI on another AI, a lightweight model that just mimics the slow physics. And the results were just incredible. Look how tightly the AI tracks the power target compared to the PID controller. How much better? 18.5 times lower tracking error. That is just a massive improvement in control.
And the speed is the real game changer here. This training took just 23 minutes. That's a 470 times speed up.
Of course, getting here wasn't simple. And this project has some amazing lessons for real-world engineering. Yeah, they ran into 5 really subtle bugs, the kind that don't crash your code, they just silently kill your results. And this brings us to a huge lesson on data quality. It's a classic garbage in, garbage out story. Their first model, trained on bad data, was a total disaster. An accuracy score of -77. That's worse than useless. But after they fixed the data collection, the exact same model got a perfect score of 1.0. Data quality really is everything.
Okay, so we have a great AI model. Now how do we get it out of the lab and into a real steel plant?
Well, you export the model, then compile and optimize it for the NVIDIA hardware that runs right there at the plant edge. The result? It's ridiculously fast. It makes a decision 22 times faster than it needs to for real-time control.
And here's the key. This isn't just for steel. This AI pattern could work for solar, cement, refineries, even data centers.
What's really cool is that this is the first publicly available framework that ties all of these advanced techniques together.
And the best part? It's all open source. You can grab the code from GitHub and adapt it yourself. So what will you build with it?